Hey everyone, and welcome to Real Analysis Lecture 5. We're going to review something that we've been dealing with at least since Calculus 1, if not before that. But we want to make sure that we all have a common concept of what composite functions are or function compositions are. So, given a function f from x to y and a function g from y to z, the function g composed with f from x to z, defined as g composed with f evaluated at x equals g evaluated at f of x, is called a composite function. And we refer to this as g composed with f. That we sometimes refer to this as g evaluated at f of x. So the composition of functions is when we evaluate one function at another function. And I will quickly add, the process of evaluating one function at another function, as we have here, is called function composition. Let's look at some examples. Just for the sake of example, let's consider these two functions. F of x equals 3x squared plus 2x plus 1, and g of x equals 1 over 3x minus 1. And let's create some composite functions. F evaluated at g of x. What we'll do here is use the outer function, f, as the function of reference. So to determine how we compute this or how we understand this, we look at the definition of f. And here we have the definition of f evaluated at x. This is f evaluated at x. What we have down here is f evaluated at g of x. So down here, g of x plays the role that x plays up here in our model or our definition of f of x. So every place we see an x up here in our model, we're going to put g of x down here. There. You see, every place that we see an x up here in our model or our definition of f of x, we put g of x down here because this is f evaluated not at x, but at g of x. When we've taken it this far, now we can use the definition of g of x. And every place that we see g of x here, we'll just put 1 over 3x minus 1. So in terms of x, this is the function f evaluated at g of x, or f composed with g of x. Well, that was easy. Let's do another one. Now, when I was in calculus, this just used to throw me for a loop. How on earth can we evaluate a function at itself? Well, the same way that we evaluate a function, it's some other function that we say to ourselves, down here, f of x is playing the role that x plays up here in our model, because this is f evaluated at f of x. So f of x plays the role down here that x plays up here in our model or our definition of f of x. So every place that we see an x up here in our definition or our model, we're going to put an f of x down here. So we'll have 3 f of x squared plus 2 f of x plus 1. And now that we've taken it that far, that we can replace f of x with the definition of f of x. Not nearly as complicated as we might want to make it, right? Okay, let's do a couple more. Let's take g and evaluate it at f of x. And remember, we're going to use the outer function as our function of reference. This is g evaluated at f of x. The definition of g gives g evaluated at x. So down here where we have g evaluated at f of x is playing the role that x plays up here in our model or our definition of g of x. So every place we see an x up here in our model or our definition of g of x, we're going to put f of x down here. So we're going to have 1 over 3 f of x minus 1. And now that we've gone this far, we can just insert the definition of f of x. And here we have g evaluated at f of x solely in terms of x. And if we want, we can simplify that. Well, we're looking good. Let's do one more. That we evaluated f at f of x, why not evaluate g at g of x? We can do that. Down here, the function g of x is playing the role that x plays up here in the definition or the model of g of x. So every place that we see an x up here in our model or our definition of g of x, we're going to put g of x down here. So instead of 1 over 3x minus 1, we're going to have 1 over 3g of x minus 1. And now that we've taken it that far, that we can insert the definition of g of x. And we can take this and simplify this to our liking. But here we have the function g evaluated at g of x expressed solely in terms of x.